Hello everyone. In the previous video we had arrived at this equation involving the unknown scalar function f as well as the unknown deflection w. So this is a single equation containing the two unknowns f and w, and so we have to find another equation. Question is, what do we do to find another equation? Because we've already proceeded by the root of the virtual work equation to arrive at this. What else do we use to arrive at another governing differential equation? Well, you see, the clue lies in the presence of this scalar function f. Alright, so the clue is like this, that back in applied elasticity, when we were doing those problems in 2D elasticity, in fact when we had derived those formulations resulting in those biharmonic equations, both in the case of plane stress and plane strain, one important thing which we had to ensure while going down the route of the eddy stress function is that we had to ensure the compatibility. Okay, because that was the stress function approach. We were proceeding via a route which would help us determine directly the stresses. So it was not a governing differential equation for the displacement that we were arriving at. Rather, it was a governing differential equation for the eddy stress function which would lead to the stresses. So in that situation, we had to actually ensure that the compatibility equations were satisfied. Now, one might argue that we do have an equation here involving the displacements. Okay, and that was and that is certainly true. But at the same time, we do have a part of this setup having the presence of this scalar function, which is working like which is like the counterpart of that eddy stress function of applied elasticity. So it perhaps makes sense for us to try to go down the route of ensuring the compatibility of the equation, and let's see how it might give us another governing differential equation. Okay, but we have to be a little bit careful here, and you'll see why the reason or why the motivation for that carefulness. Okay, so let me go to the new page and start off. The specific compatibility equation that I'm going to deal with is this one, del square epsilon xx. I'm not going to the details of this too much here because these discussions were already we'd already had these discussions back in applied elasticity. So I'm just going to utilize this. So we have this compatibility equation. Okay, now if you are a little bit observant, you should immediately point out that we have written down this compatibility equation, but it has no real place in this particular theoretical development. And the reason is that here we are actually using not these small strains or these infinitesimal strains, rather the large strains, which do involve the nonlinear terms. So what do? We should not directly be using these, or so no matter, what we'll do is we'll simply write down the connection between the small strains or these infinitesimal strains and the large strains that we're actually dealing with. So we note that Exx, this is the one which we are really interested in as part of our formulation, and that is just the infinitesimal strain added by this extra term. So you can easily see this if you go back to the very first page, or perhaps the second page of these lecture slides. In terms of the videos, it was present in the first part of the introduction and derivation part 1 of the von Kármán plate theory series. Okay, next for the EYY, we have epsilon YY plus half del W del Y square, and for EXY we have its connection with the epsilon XY in this fashion. That's it. So all that we have to do is to go back to this compatibility equation and substitute these epsilon xx, epsilon yy and epsilon xy in terms of these exx, eyy and exy. Okay, so so from here what we are going to obtain is this thing. So I'm skipping a step here. Del square Exx del y square minus of del square del y square of this entire thing. So that's the first term. For this second term, we'll have del square Eyy del x square minus del square del x square, and then this term. And on the right hand side, we are going to have del square Exy del x del y minus twice del square del x del y half del w del x del w del y. So basically this term. Okay, now this looks like a horrible mess. It is going to become a little bit simpler, but first we have to note that we don't want to keep it like this, because within this Exx, if you go back to the earlier pages, you'll see that we have already expressed this Exx in terms of the Exx naught, which was independent of the any z dependence, and the other terms which had some z dependence. Okay, so let me just go back and so sorry about that. So we had these relations. So Exx is equal to Exx naught minus z del square w del x square, and similarly for Eyy and Exy. So this is what we are going to utilize. Now if we do that, okay, if we do that and expand and simplify, what we are going to end up with is something like this. Let me get back to this page. So if I do all that, I'll end up with so let me write that down first, and then I'll discuss it a little bit. Okay, you see, in going from this step to this step, it is not something that I have done mentally. Again, I have written this down in a piece of paper separately, and then I have just copied from there, because going from here to here, it is not just a matter of substitution of this Exx in terms of this Exx naught and the other terms. Rather, there is a considerable amount of simplification going on in these terms involving the w's. Okay, so it's not just a trivial one-step affair in going from this step to this step. You do have to go through a few steps and do some simplifications in order to arrive at this. Okay, so what I'm going to do is I'm going to give this part this particular simplification, going from this step to this step, as an exercise in your problem sheet, and you can do that. Of course, there's not much mechanics involved in that. There's no mechanical understanding. It's just simple calculus and algebra. So I believe all of you can do it on your own. So let me move on to things which do involve advanced mechanics of solids, and which will ultimately help us to obtain the governing differential equation. All right. So going to the next page, how do we proceed from here to the governing differential equation? Because you see, my motivation here is not to just play around with this compatibility equation. My motivation here is to use the compatibility equation to somehow arrive at terms which would help me obtain an equation involving this W, which I already have here, but also involving somehow the F. Okay, remember that F, the scalar function which we had obtained in the previous, or which we written in the previous video. So that one. So I want to arrive at an equation involving the F and the W. I already have one equation, so I want to end up finally with two equations involving the F and W, so which I can solve simultaneously. So how do we go from here? Well, the clue is here in the through these terms, the Exx naught, the Eyy naught, and the Exy naught. By themselves, they do not have any connection with the F. But suppose we were to write these in terms of the sigma xx, sigma yy, and sigma xy, and then perhaps there would be some hope of carrying out the connection or link or establishing the connection with the F. Okay, so let's proceed a little bit. What I'm going to do next is to reconsider the expression for the nx. Okay, because that actually contains within it the sigma xx, and we'll see how we finally make this connection with the Exx naught, etc. So this is what we have now. This sigma xx, using the constitutive relation, I have this as, so sigma xx is e by 1 minus nu square Exx plus nu Eyy. So again, I am using whatever we had discussed back in our chapter on 2D elasticity from our course of applied elasticity. Okay, so if you have forgotten those things, the kinds of reduced constitutive equations that we obtained in the case of the plane stress, and the reduced constitutive equations that we obtain in the case of plane strain, I strongly advise you to please go back to those video lectures and take a look, and I'll try to put in the link in the video description below. All right, so once we have these things, we can hope to make a connection with whatever we had written in the previous page, because we know that this Exx is Exx naught minus z del square w del x square, and this one here can be written as Eyy naught minus nu z del square w del y square dz. Okay, now again you note that this particular term by itself, the del square w del x square and the del square w del y square, because w is a pure function of x and y, that can come out of this integration with respect to z, and this z and this z is the only thing remaining, and that if you integrate from minus h by 2 to h by 2, that will just give us a 0. So effectively this gives us a 0, this gives us a 0, and what will be left with in the next step is just this term. All right. Now, what we are going to say is that, you see, this Exx naught and Eyy naught, they are independent of z. So we might as well take them out of this integration. And if we do that, then what will be left with is this integration minus h by 2 to h by 2 dz, and that is nothing but h. So ultimately what we arrive at is this EH divided by 1 minus nu square Exx naught plus nu Eyy naught. And what we say is that, just like in the classical plate theory, we had arrived at a term like EH cube by 12 1 minus nu square. We had called that as D, the bending rigidity. So also this thing we will just write as C. Okay, so overall this Nx is C Exx naught plus nu Eyy naught. Alright, okay, so this was about Nx. In exactly the same fashion, we can arrive at similar expressions for Ny and Nxy. So let me just, without going through all these details, let me just go to the next page and write those things together. So Nx is equal to C Exx naught plus nu Eyy naught, and y is equal to C Eyy naught plus nu Exx naught, and Nxy is equal to C into 1 minus nu Exy naught. Now all that we have to do, because you see our ultimate motivation here is to go back to that version of the compatibility equation which we had left earlier, so this equation, and we want to rewrite these Exx naught, Eyy naught, Exy naught in terms of this Ny and Nxy. So now all that you have to do is invert these relations. Okay, so if we just do a little bit of algebra and invert these relations, what we are going to obtain is Exx naught is equal to Exx naught is equal to 1 by EH Nx minus nu Ny Eyy naught is equal to 1 by EH Ny minus nu Nx, and Exy naught is equal to 1 plus nu in the numerator divided by EH multiplied by Nxy. Okay, so now if we just take these expressions and substitute them in that earlier equation, meaning this equation, okay, if we just substitute here, let me just try to copy this thing. So substitute in the following. Then the equation that we are going to end up with, okay, so that is not a very complicated step. I'll just write it down. So I can utilize this page itself here. So I'll end up with 1 by EH. Sorry about that. One by EH del square NX del Y square minus nu del square NY del Y square. So from this one and substituting these things, next substituting the EYY naught from here, I'll obtain del square NY del X square minus nu del square NX del X square, and then minus 2 1 plus nu, so basically this one, del square NX Y del X del Y. Close the square bracket, and on the right hand side whatever I have here, I just write that. Okay, so del square W del X del Y, square of the whole thing, minus del square W del X square del square W del Y square. So all that I have to do now is to just go back and look at the expressions for this nx, ny and nxy in terms of the scalar function f. So this nx was del square f del y square, and y was del square f del x square, and this nxy was minus del square f del x del y. So if you substitute that, okay, so substitute all these things, then the equation that we are finally going to obtain is the biharmonic of f. Okay, so again, I'm not doing this by one mental, I'm not just doing this mentally in one step, but I have already done this thing, so I know what the expression is. So this is, it ultimately simplifies to this biharmonic of f is equal to EH. So that EH goes to the right hand side, and whatever is present here. Okay, and now you see, starting from the compatibility equation, we have arrived at this this other governing equation, which also involves both this unknown w as well as this unknown scalar function f. So let me let me just put this within a box, because This is the governing equation that we wanted, the other governing equation that we wanted. So now if I go back, this was the first governing equation. So please note that this is referred to as the first Föppl-von Kármán equation, and this one is referred to as the second Föppl-von Kármán equation. So whenever we have to solve a problem where there is a possibility of some buckling, then we have to deal with both these Föppl-von Kármán equations simultaneously. Please note that in this entire thing, I have not actually gone back and taken a look at the so just hang on, at the boundary terms. So I will end up with certain boundary terms also. Okay, you see that I have just written down the governing differential equation here by considering this overall thing. I have not actually considered these boundary terms here. They are left unconsidered. So it is only when we deal with certain specific problems that we'll have to deal with those boundary terms. At this point, I do not want to write those down in their full generality. Okay, but the most important thing is that unlike classical plate theory, where we arrived at a single equation involving the deflection, here in the Föppl-von Kármán plate theory, we have two equations involving both the W and the F. You also please note that if I just consider this first, the first Föppl-von Kármán equation, then this here, these are the extra things present really. Compared to the classical plate theory, these are really the extra things which are present. Please note that I just noticed that there is a little bit of a sign mistake here, and that goes back to the previous video also. I'll just correct it very quickly. So back when we were doing this, so you see that on the second part of this LHS there was this minus sign, and on this first part of this LHS also there was this minus sign on this term, this outside minus sitting here. So when I wrote the governing differential equation, the third part here, which was the coefficient of delta W, there should really have been a minus sign in front of all of these. Okay, so there should have been a minus sign in front of all of these. So I'll just correct this, and there was this mistake on the right hand side, which I had corrected in the second step, that this Q was absent. Okay, so I'll make this correction in the next step also. Sorry about that. All right, so if we proceed like that, well, there will be a minus here also. There will be a this will be within the bracket, and this thing, well, I had simplified it a little bit. There would be a minus here, and now when I substitute this thing, I would have a minus here. But since I already have this thing with a minus, all these terms involving the m, and this itself is a minus d del 4w, so this would become a plus. Okay, so the first of the Föppl-von Kármán equations, well, this comes with a plus here, and this is a minus. This also is a minus, and of course this is a plus. All right, so with this correction we have the two Föppl-von Kármán equations. This is the first one, and as we have just derived it, this is the second one. So on that note, I'll end this video. Thank you very much.